All right. So how's the undetermined coefficients going? I know, Thea, you mentioned earlier that the algebra is pretty brutal.
Oh, yeah.
But beyond the algebra, how are we feeling about the process of undetermined coefficients?
I mean, it's pretty straightforward. There's just a lot of it, you know?
Yeah, and what really makes undetermined coefficients kind of nasty is what that forcing function's equal to, what that f of t is.
Yeah.
Right? Because if f of t is simple, it's no big deal. It's when you start getting, t squared e to the t sine of 4t, that then, as you differentiate, of course, you have to do product rule upon product rule, and you get just a butt ton of variables that you're later going to have to do. With that said, are there any that you want to look at from the homework?
There is one. It's 37b on 5.5.
All right, let me go find that here. So 37b.
Yes.
All right, let's see.
Isn't that on 5.4?
No. It's on 5.5. It's
Wait,
like the
no,
final
that is
question.
Oh, hold on there. So, because I'm like 37.
Oh, wait, sorry, 5.4. Yeah, it's 5.4.
Okay, because 37b was second part of a nasty proof that there's no way I would have given to you because I'm not that big of a douche. All right, let's see. So 37b, it says, right, y equals u e to the alpha x to find the general solution.
Yeah.
Okay, let me rewrite this guy real quick, and then we'll go to the board. So we have y double prime plus 6y prime
plus 9y.
9y is equal to e to the minus 3x
times natural
log of x. Yeah. Okay, so let's switch to the board. And Monty is back.
Hey.
Okay. So it said, let's go ahead and write y equals u e to the alpha x. So we should probably figure out what alpha is. And in this case, if we go ahead and do our little polynomial, we're going to get r squared plus 6r plus 9, which gives us r equals 3. Or sorry, minus 3. So we're going to be looking for a form y equals u a to the minus 3x. All right, so far so good?
Mm-hmm.
All right, so now let's see if we can figure out what that's going to make u have to be. So let's go and get y prime and y double prime. So y prime is going to be u prime e to the minus 3x minus 3u e to the minus 3x. And then y double prime is going to be u double prime e to the minus 3x minus 6 u prime e to the minus 3x plus 9 u e to the minus 3x. All right, so there's our derivative and our second derivative. So let's go ahead and put those in and see what falls out. So y double prime, u double prime e to the minus 3x minus 6u prime e to the minus 3x plus 9u e to the minus 3x. We're going to add 6 y primes. That's going to be plus 6 u prime e to the minus 3x minus 18 u e to the minus 3x. And then we'll go ahead and add 9 of the original function. So it'll be another 9 u e to the minus 3x. All right. So far so good.
Mm-hmm.
And of course that's going to equal the e to the minus 3x natural log of x. All right, well, this one's really nice because almost everything goes away. All the u primes and all the u's go away. So now we've got u double prime e to the minus 3x equals e to the minus 3x times natural log of x. So really what we just did was we reduced order. But this one's actually awesome because if we divide by that e to the minus 3x, we've got u double prime is equal to natural log of x. And this one's going to be really quick and easy to find u.
True.
Because all we're going to have to do is integrate twice. All right, well, let's see what that ends up being. All right, well, if u double prime is equal to natural log, then u prime, excuse me, is going to be x natural log of x minus x. And I'll go ahead and just put a plus c1. So I just remember what the integral of natural log of x is.
Mm-hmm.
But how could you do that if you didn't remember and you didn't have, say, you know, your technology? What process would you
By
do?
parts.
Yeah, it'd be integration by parts. You'd let u equal natural log and then go from there. Okay, well, there's u prime, which means we need to do one more integral. So we have to integrate x natural log of x. That's going to be another one that requires parts. Let's see if I can do that in my head. X squared over 2. So we'll get an x squared over 2 natural log of x minus x natural log of x plus x. He says with a question mark.
Here.
No, that's not quite right.
Integral of x ln x minus x. 1 half x squared ln of x minus x squared over 4 minus x squared over 2.
X squared over 4. And then you said minus x squared over 2 or plus?
Minus, both minus.
Okay, so that's the integral of x log x.
Yep.
Okay. And then of course we're going to get our minus.
Oh no, yeah, no, that was the whole one. That's the
Oh,
whole
okay, because that's the integral of the x. It's x
Yeah.
squared over 2. So then we're going to get c1x, and then we get to add another c. Okay, but we're not done because that's just u. But remember what u was. It was the integrating factor. So from this, we can write then that our solution is going to be, again, it's u times e to the minus 3x. So we'll just multiply that by e to the minus 3x. And so we get x squared over 2 natural log of x e to the minus 3x minus x squared e to the minus 3x over 4 minus x squared e to the minus 3x over 2 plus c1 x e to the minus 3x plus c2 e to the minus 3x. And there's your solution. So check it out. Remember what the roots were, right? The roots were -3 repeated. So that tells us that we should have an e to the -3x and an x e to the -3x in our fundamental set. And they still showed up. They still showed up through this process. It's just now we also have the particular solution. So if you were to break this down into kind of the language we used before, all of this is our particular solution. And then the other bits, that's from our fundamental set. I'm going to call it y sub h for homogeneous. But there's that guy. All right, so okay for this one?
Yeah. It's just where to get started, I guess. There's like, I've learned with like doing all these problems, it's just, with certain problems, it's just hard to guess at the y particular. But I guess that's where the y times u y1 comes in, so.
Absolutely, because like this one, there is no way to recognize that our guess for a particular would be this form. That it's going to be some, you know, polynomial times e to -3x, and then also some polynomial times natural log. Like the chance of you spotting that is near zero. But whenever you know a root, right? Whenever you know y1, you can always try some integrating factor, because if nothing else, it should reduce the order, because we saw that last time. And this one was actually huge because it basically reduced the order by 2. Right? It started as a second order, but then ended up really being a 0th order, because we could literally solve for y double prime, which then just required some integration. All right, so good for 37B?
Yep, so much better.
Okay, cool. All right. Any other ones from the homework?
Can we do number 8 on 5.5?
That was number 8?
Yes.
Okay, so 5.5, number 8. Okay, let me go see what that looks like. All right, so for this one, all it says is find a particular solution. And they give us a differential equation. It just looks like this. So we've got y double prime plus y. And that equals -4 plus 8x times cosine. And then plus 8 minus 4x times sine. All right. So we just want to solve this guy. So where should we start? What should you always start with?
Y equals u e to the, no, never mind, that's the wrong one.
Yeah, we don't want to go there just yet. We might. But yeah, so JP just said solve the homogeneous. So let's start with that. So if we look at this one, this is going to be r squared plus 1 equals 0. So we get r equals plus or minus I. So then that tells us what our solutions are going to look like. The y1 and the y2 are going to be cosine of x and sine of x. And they can be in either order, of course. But since r is equal to plus or minus I, then we know that we've got sines and cosines. All right, but that was necessary for us to make our guess. Because let's think about what our guess is going to be. So we've got a polynomial times the trig, which means that's what we want in our guess for our particular. So I want ax plus b times the cosine of x plus cx plus d times the sine of x. All right, give me a second here, guys. I need to silence my phone. Okay. All right, so far so good. But unfortunately, this isn't enough. And you may have noticed I left a little space here. We are going to need to multiply by x. Do you see why?
Because cosine and sine are in your solutions, your y1 and y2.
Yeah, you think about distributing this. I'm going to get a b times cosine of x, which I already know is going to do nothing because that cosine is part of my fundamental set. So the b times it is just going to give me 0. And then similarly with the d times sine, we have the same problem. So what I need to do is I need to multiply by x. So you may remember that last time I showed you that what you need to multiply is, well, I called it t, but tx doesn't matter. But I said it was like t to the s or something, where s can change. But basically, we're going to use whatever power we need so that when we multiply through, none of these things are in the fundamental set. So that's why we got to solve the homogeneous first. Not only do we want it for the end, right? Like we need that at the end, but we also need it to recognize that that x needs to be here. All right, so before we go ahead and get a solution here, are we good with the guess? Mikey's giving me a thumbs up. All right, thanks, JP. And JP, you're in a new place. I don't recognize the background. He's going to explain why he's in a different location, I think. Anyway, all right, so here's our particular. So now let's differentiate and see what we get. The laptop. All right, so we need to differentiate because we really need to get to the second derivative. So think of this as ax squared plus b times cosine. I think it'll be a little bit easier. That way we don't have to do product of product. And then this other one's going to be cx squared plus dx times sine. Okay, so here's y prime. It's 2ax plus b times the cosine of x minus ax squared plus bx times the sine of x. And then when we differentiate sine, or the other piece with the sine, we're going to get 2cx plus d times sine of x, and then plus cx squared plus dx times cosine.
Never mind.
So those bottom two, that's the, again, product rule for the second piece.
No, you didn't.
Then
Never mind.
I listed them this way so that we've got all the cosines together and we're going to be good. So JP, did I just hear a never mind? You caught Y? Okay. All right, so let's get our Y double prime. So Y double prime, we differentiate these bits, we're going to get 2a plus 2cx plus d times cosine, and I get minus 2ax plus b plus cx squared plus dx times sine. So the minus came from the derivative of cosine. And then we're going to get plus 2c minus 2ax minus b. Oh, I need that over here. Sorry. 2c minus 2ax minus b times the sine of x and then differentiating the sine gives us a minus cosine, so I'll put a minus 2cx plus d minus ax squared minus bx times cosine of x. So I think that's right. I'm not terribly confident right now, but I feel like we're good. Okay, so let's go back to the original differential equation, and we're going to take y double prime, and we're going to add to it the y. So I'm going to erase my y prime because we don't need that anymore. And again, I'm going to lump things in terms of sine and cosine. Okay, so y prime plus y double prime. In terms of cosines, I'm going to get ax squared minus a negative a squared. So that's going to be a plus. So we get 2ax squared. In terms of the x's, I've got b plus 2c minus a negative b. So the 2c's are going to cancel. The minus a negative b is a plus b, plus the original one I think is plus 2b times x. And then in terms of our constants, that's only what we've got left down here. So it's going to be 2a plus d minus d, which I think is just 2a. So I think that's all the bit on cosine. So then let's go to sine. With the x squareds, I've got cx squared minus cx squared, so that's gone. For my x's, I've got minus 2a minus d plus a minus 2a. So I believe that gives us a minus 4a plus d. So that's our x's. And then our constants, there were no constants here. Oh, hold on, the d is gone. Because we have a minus d plus that d. So those are gone. So in terms of the x's, we just get the minus 4a. Okay, I like that better. And then the constants, I'm going to get b plus negative b, so those go away. And then I've got a plus 2c. So that's our y double prime plus y. So we need that to equal what's over on the other side. So here's how this is going to play out. We're going to get 2a has to equal 0. We've got a problem. I've got a problem somewhere. Crap. That suggests 2b is equal to 8. Because this also suggests then that 2a is equal to minus 4. Since this has to equal 8x minus 4. I think what happened, you have to go back and look because I've erased everything. I think the x squared should have canceled. Maybe you guys can double check that for me. Anyway, so then for the other side, we're going to get minus 4a equals minus 4 and 2c equals 8. I know I messed up somewhere because these three are all a problem. I either have 2a equals 0, 2a equals -4, or 2a equals 2. And it definitely can't equal all of them at the same place. So my guess is that somewhere along the way, I did a derivative wrong. And like I said, it's been long since erased.
It's okay, Bruce. I'm good from there anyway.
Okay, so hopefully somewhere you can figure out where the problem came about. But what we should end up with are values for A, B, C, and D. And then we'll know exactly what our particular solution is. All right, so sorry about that. All right, anything else from the homework? Cool, then I don't have to be in algebra hell anymore. All right. So what we're going to do today then is continue our discussion on variation of parameters, because I showed you one example, which is not nearly enough. I want to show you a couple more, just so you can see the process. But the beauty of the variation of parameters is it will always work as long as we know the fundamental set. If we know y1 and y2, we're good to go. So let me remind you how that worked. So we'll come back to the board here. So what we did last time was we went to the, suppose that we know y1 and y2. So I'm just going to write here, so suppose that we have the fundamental set. And sometimes that's easy, right? Like when it was the constant coefficients, we know how to find those. Sometimes it's not so easy. But if we've got them, then what we did was we guessed the form y equals u1 y1 plus u2 y2. So we start with that guess, and then we put a restriction on this. We said that u1 and u2, they have to be such. So, hold on. So with the restriction, and we chose this restriction of u1 prime y1 plus u2 y prime y2 equals 0. And at the time, it probably felt like a miracle step, and it definitely was. But it ended up making it so that things simplified down easily for us. And what we found is that if this is case, if this is what we have, then it follows that we have another equation involving u1 prime and u2 prime. And we saw that it was that u1 prime y1 prime plus u2 prime y2 prime had to equal f of t, where f of t, that's what our function was equal to, our differential equation was equal to. And this led to a system of equations. And what we saw was that we could turn this into a matrix equation. And we recognized that this matrix was the Wronskian matrix. And what we know about the Wronskian matrix is that it's defined and that it will have an inverse because its determinant is non-zero since y1 and y2 are linearly independent. And what that meant was that we could then solve this for u1 prime and u2 prime. And what we saw was that u1 prime that was equal to negative y1 times the function f divided by the determinant of the Wronskian. So let me just put Wronskian here. Did I write y1? I meant y. Okay, so that was our u1 prime, and then u2 prime was equal to y1 times f of t over the Wronskian. And so then once we had u1 prime and u2 prime, we could go ahead and integrate those things and we'd be good to go. All right, so that's what we developed last time, right? We went through the process, we built that thing, or we saw how to do the solution. And then I went ahead and I showed you an example. We did one that, well, I have no idea what the answer was or what it was equal to. It was something with like a cosecant or some nonsense.
Yeah, weird. We got ln, cosecant, cot.
Yeah, so we can really just have it be, now we can have this f of t be anything. And it's going to work out. So this is a perfectly viable process as long as we know y1 and y2. If we do not have a fundamental set, this will not work for us whatsoever. All right, well, let me show you some examples, a couple more examples here to remind you how it works and to show you why we like it. And then we'll talk about, is this a good choice, a bad choice, you know, kind of depending upon what our differential equation is. How do you choose which method to do? Because we've seen three now, right? We've seen really the undetermined coefficients where we make our guess. We've seen reduction of order, which is we know one of the solutions in the fundamental set. And then there's this one that requires both. But let's try one here, just to kind of remind you how this works. And let's see how this goes. So we're going to have y double prime minus 2y prime plus y. And let's let that equal e to the t over 1 plus t squared. All right, so looking at that, you should probably rule out undetermined coefficients. Because trying to make a guess of what might give us a solution of e to the t over 1 plus t squared is probably challenging. I think you'd probably be willing to say that the particular solution is going to involve some sort of e to the t. It's probably also going to involve some sort of a either natural log, because natural logs tend to give us things on the bottom when we differentiate. Maybe an inverse tangent because of the 1 plus t squared. Maybe some sort of 1 plus t squared to a negative power, you know. But this is the problem, is we don't know. It's not something really clear. So instead, we'll turn our attention to another process. But this is one that we can find the particular set, or the fundamental set quickly, because of the fact we have constant coefficients. So if we make our polynomial, looks like that. That gives us r equals 1 repeated. So y1 is going to be e to the t, and y2 is going to be 2, or sorry, t e to the t. All right, so since we know a fundamental set, variation of parameters is a perfectly viable option. So let's do it. We do need to know the Wronskian. So let's go ahead and create that matrix and find its determinant. So I'll just call that matrix W. So the Wronskian, the way we find it is we put the two functions that are in our fundamental set in the first row. And then the second row, we just take their derivative. So it's going to be e to the t, and then e to the t plus t e to the t. But we really need the determinant of this matrix. Well, that's going to give us e to the t times e to the t, so e to the 2t, plus t e to the 2t minus t e to the 2t. So those are going to cancel. So that's actually our Wronskian, e to the 2t. So do you guys remember Bobbles Theorem? Or at least the name? Bobbles Theorem showed us another way that we could have gotten the Wronskian off by at most a constant coefficient. And you actually find that by doing e to the negative integral of p of t. Well, if you integrate minus 2, you get minus 2t. Make it negative, that's plus 2t. And you'll notice that our Wronskian was e to the 2t. Just throwing that out there as a reminder of how that worked. Because sometimes that's faster than actually going through the process of creating a matrix. Let me write it up because I just said it in words and some of you see it better than hearing it. So there was this Bobbles theorem that said the determinant of W, it's some multiple of, so I'll just call it K times e to the negative integral of P. And that's all I did here. If that was negative 2, so from Bobbles theorem, we know that the Wronskian is some multiple of e to the 2t. Turns out in this case that multiple is 1. But anyway, Bobbles theorem, that's aside. All right, well, we've got our Wronskian, which means now we're ready to figure out what U1 and U2 prime are. So let's just jump up here. So U1 prime is going to be negative Y2, so negative T e to the T, times F, which was e to the T over 1 plus T squared. And then we need to divide by the Wronskian. And similarly, U2 prime is going to be Y1, which in our case is e to the T, times F, so e to the T over 1 plus T squared. And then again, divided by the Wronskian. So if we just do that algebra real quick, we're going to find that U1 prime is equal to minus T over 1 plus T squared. The e to the 2t cancels with the e to the t times the other e to the t on top. And then similarly, U2 prime is just going to end up being 1 over 1 plus T squared. All right, so we're close. Now we just have to integrate those things. So U1 is going to equal negative natural log of 1 plus T squared. and then divided by 2. So you can get that just by doing u substitution, right? Let u equal 1 plus t squared, and we'll be good.
Isn't
And
the
then-
second one arctangent?
Sorry?
Or isn't the second one arctangent?
And it is, yep.
Okay.
U2.
I was just making sure I was remembering correctly.
That's going to be the inverse tangent of t, arctan of t. Good old form, 1 over 1 plus x squared, 1 over 1 plus t squared. Okay, well now we're ready to write what our solution looks like. So we're going to get y equals u1 times y1. So we're going to get this times y1, which was e to the t. So we're going to get minus e to the t natural log of 1 plus t squared over 2. And then we're going to get u2 times y2. y2 was t e to the t. So we're going to get plus t e to the t inverse tangent of t. And then, of course, we need to add on our c1 e to the t and c2 t e to the t. That came from our fundamental set. Okay, so our particular solution is that right there. And like we talked about, it's definitely got an e to the t, which we kind of figured, but I don't think any one of us would have guessed that this is what the form would have to look like for a particular solution. But the beauty of this is that you don't need to do that. As long as you can find y1 and y2, we have a process. So one other thing, just to kind of mention, because when I found my u1 and u2, you notice I didn't put c's, but we could have, and it would have given us exactly the same thing. Like, what if I'd written plus c1 and plus c2 on those respective pieces? Remember, what we do with those u's is we multiply them by their respective y's. So we would have had y1 times c1, which is that c1 e to the t. And then this one we would have had y2 times c2, which was the c2 t e to the t. So it would have been caught. It would have worked out either way. All right. So what do you think? So far, so good? All right. So super nice when it's something that's easy to find the particular, the fundamental set. But that's not always the case. But as long as they're given to you, you can still find it. So I'm going to give you one that's a little bit nastier in terms of trying to find a fundamental set, but I'll tell you what the fundamental set is. But let's look at this guy. So we've got x squared y double prime minus 3xy prime plus 4y. And let's make that equal x squared natural log of x. All right, so this is another one where trying to make a guess of what the form would be might be a little difficult. But even worse, trying to find a solution set to the homogeneous, we don't know how to do that yet. Later, you'll learn how to solve these guys. These are called Euler equations, and there is a process for those. But for right now, you guys are kind of SOL. So let me tell you them though. Let me give you a fundamental set. So the first one is just good old x squared. And you can probably see quickly that that works. If you differentiate it, you get 2x. Differentiate it twice, you get 2. So when you plug it in, you're going to get x squared times 2 minus 3x times 2x plus 4x squared, and that does equal 0. Now, the fact that I gave you 1 means you can find the other, because you can do reduction of order. But I'm going to help you out. I'll go ahead and do that for you. And say through reduction of order, you find that the other one is x squared natural log of x. So you do a u equals x squared, take some derivatives, blah, blah, blah. Turns out that, find out that u has to equal natural log of x. All right. So what we need then is the Wronskian, or at least a scalar multiple of the Wronskian. But let's actually look at Bobbles theorem, what Bobbles theorem tells us, and we'll also do it the long way. So if we do it the long way, here's our w. Our w is going to have x squared and x squared natural log of x. The derivatives are going to be 2x, and then 2x natural log of x plus 1 over x, or nope, sorry, just x. And so if we find the determinant of that, that ends up being x cubed. So it turns out it's pretty nice. Well, let me really quickly show you, well, yeah, let me show you Bobbles theorem. So remember, Bobbles theorem, we need to take e to the negative integral of p. But this is where you got to be a little careful, because we have that x squared out front. We have to divide by that x squared. So this would also look like y double prime minus 3 over x times y prime plus 4 over x squared times y equals natural log of x. And so according to Bobbles theorem, we know that the Wronskian is going to be some multiple of e to the negative integral of negative 3x. So this is going to give us ke to the 3 natural log of x, which if we bring that 3 in, tells us it's some sort of k times x cubed. So again, turns out k is 1, but this is an alternate approach, another way of actually finding the Wronskian. What you'd have to do, though, when you actually want to find k, if you were to put this into the process and get your u1 and u2 equals, it would have a k in it, but you could figure out what those k's have to be to make it match the other side, and then you got it. But we already got it. We already got x cubed. Okay, so Bobbles theorem at least checks out. But let's go ahead and find u1 and u2. So u1 prime can equal negative y2, so x squared natural log of x, times f. Okay, well in this case, that's going to be natural log of x again. So this is another reason why we needed to divide by the x squared. Had we not, that would have suggested that the f would be x squared times natural log of x, and then all sorts of bad things would happen. Because when we developed this process for u1 and u2, it required the y double prime being by itself. Okay, well, we do have one more thing we got to do. We have to divide by the Wronskian. So u1 prime is negative natural log of x squared divided by x. All right, so there's u1 prime, which while we're here, let's go ahead and get u1. So if we integrate that, this would be a u sub where you let u equal natural log of x. And so this ends up being minus natural log of x cubed divided by 3. The over x comes from the chain rule on the natural log of x. All right, well, let's get u2 then. So u2 prime, that's going to equal y1, which was x squared, times f, so times natural log of x, divided by the Wronskian, which is x cubed. So u2 prime is just natural log of x over x. Well, that's another really quick u sub if you let u equal natural log of x. So we get the natural log of x quantity squared over 2. All right, well, let's multiply those by y1 and y2, and we'll be done. So what we've got then is that y equals u1 times y1, so minus x squared natural log of x cubed divided by 3 plus u2 times y2. So u2 was x squared times the natural log of x. And again, so that's going to be times natural log of x quantity squared over 2. And then, of course, plus our c1x squared plus c2 x squared natural log of x. And I'm going to do one more thing just because I can. These are like, they're both x squared times natural log cubed. So I'll take the 1/2 minus a third, which gives me a 1/6. So we get x squared natural log of x quantity cubed over 6 plus c1x squared plus c2x squared natural log of x. So I highly doubt that anybody would have looked at this y and went, oh yeah, that's the one that when we put in this differential equation will give us an x squared log of x. But like before, it turns out it's not necessary to have made a guess. We can actually find it using variation of parameters. All right, so how are we feeling about that example? I will take everybody's silence as we're all good. Okay. All right. So that's variation of parameters. It is what it is, but it's a good process. It always works as long as you know y1 and y2. If you don't know y1 and y2, you got no chance. All right. So how do you decide which method to use? Well, first of all, undetermined coefficients only works with nice forms for your f, right? So if f is not polynomials, exponentials, or trig, and trig I mean sine and cosine. So if it's not one of those three forms or products thereof, don't try undetermined coefficients. Unless you're really good at spotting what general form should be. Okay, so that means if it's something gnarly like x squared natural log of x,
we have to do either reduction of order or variation of parameters. I pretty much only use variation of parameters if I know both in the fundamental set. So it has to be a really nice form for me to get there. Or alternatively, if I can find one easily, and then I don't mind doing a little bit of integrating factor to try to find the other. Like in this example, I might have done that, given an x squared, gone, okay, well, let me find my other one. But usually, instead of that, I just go straight to reduction of order, because the process involved for finding y2, knowing y1, is part of the process for doing variation of or reduction of order. So if I'm going to already go through all that work just to find my y2, I might as well piggyback on that and just finish it out as a reduction of order problem. Okay, so really it comes down to, can you find the fundamental set easily? If so, do variation of parameters. If not, find one. Do whatever you can to find one, and then do reduction of order. All right, well, there you go. There are all the techniques that we're going to learn for solving second order. So what we're going to do next, we're going to turn our attention to applications. We're going to revisit some stuff from physics, like, for example, springs. But what we're going to account for this time is loss of energy due to drag and friction, right? We're going to look at circuits. This time we're going to put in induction. I think you guys mentioned that you didn't actually talk about induction in physics. So I will give you kind of the crash course on that, a little bit about what it is and how it behaves and why it leads to these second orders. But we're now going to be able to do circuits that involve capacitors and resistors and induction. And so once we tackle that, we've got every kind of circuit possible. So for those of you that are planning on going into electrical engineering, you're going to really appreciate where we're heading. I can see Thea is totally psyched. She just gave me the rock on. But now you've got the tools, the math tools, to allow for that. It also will allow us to do things with like objects falling through air with drag, where we have other things involved, like what if there's a fan blowing upward on our object as it's falling, right? As soon as you change that, it makes it that we can't solve it the way we did before. We're going to need other things. So basically, we now have the tools to tackle just about any mechanics problem. Since acceleration is a second derivative, they naturally lead to second order differential equations. So that's where we're going to be going next time. But that'll be next time. To be honest, yeah, we'll do